Um, and so we see this in space all the time. You just have a large cloud somewhere for whatever reason. They're all over the universe. And eventually, if it's cool enough, it'll start to contract because gravity will just pull everything that's not near the center towards the center. And so even if it's a very slow process because it's really spread out, you just sort of get that effect. And then on average, it's got some rotation axis just because the statistics of these things work that way. Anytime you have a large cloud of atoms moving, even if their average is very close to zero, on average, they'll still have some rotation. And they're enormous. And so just like when an ice skater, when she pulls in her arm, starts spinning faster, that's what happens to matter that compresses inside a cloud of gas. It spins faster. So this one, if this is the axis of rotation for this thing, then it would compress along this line. And so we talked about this before. It would eventually look like this. That was terrible, right? Galaxies sort of look like that edge on. That's how stars form. And so in the center, you would get a star somewhere. And then in here, you would get planets. And this is a picture we're sort of studying for how solar systems form. Originally, we only had one, even up to like 30 years ago, we only have one example of a solar system, but now we've got a lot of them. We can now see planets around lots of other stars, thousands of other stars. And so we're developing data for seeing solar systems in all states of formation. It's like the example I talked about in class where you land on the Earth, but you only have 5 minutes to be there. How would you figure out what the human life cycle was, right? It's challenging to do that. You might think there were just these little people and big people, but if you study it carefully enough, you can sort of figure out what's going on. And so what happens is this cloud of gas pulls itself in gravitationally and shrinks along the axis that's perpendicular to how it shrinks along its rotation axis. It shrinks this way. And so near the forming star, sort of in this region where we see the terrestrials, only rocks and metals can form solids because the others just evaporate. It's past their boiling point. And so, so here we get these small terrestrial planets. And then far from the star, hydrogen compounds can form solids. That's like we're talking about like water, ammonia, methane. And there's just tons of those. There's so much more of those than there are rocks and metals in the solar system that, that you can get giant planets. Am I off the screen? I'm right at the bottom. Okay. And so this is sort of what we see. This is the nebula. By the way, the word nebula just means cloud in Latin. So the nebular hypothesis is to say these solar systems form from clouds of gas and dust. The nebular hypothesis is consistent with the motion of the planets as well. Remember, we came up with, when we first looked, all the planets are orbiting the sun in the same direction. That's consistent with this picture that we just drew. They're all more or less in a plane, right? And which is also consistent with this picture. And so all of the physics of this stuff sort of hangs together. This hypothesis was come up by like a philosopher in the 1800s, I think. There were lots of ideas, but this is the only one that sort of survived the scientific process of the last 200 years. And now they're just ironing out the details of it. So planets form by first tiny rocks forming, right? So you've got this cloud of gas and dust. Well, eventually that stuff just clumps together and you start getting tiny rocks. And then those rocks eventually glom together, either just gravitationally or bumping and sticking. One of the astronauts in the 1980s did a really nice experiment where he took a plastic bag full of salt and showed just a Ziploc bag and showed that it clumps up in space. It's got no gravity kind of holding it onto the ground. If you just hold it out in space in an open baggie, you'll get little clumps. The matter tends to want to stick together a little bit when it's out in the vacuum of space. And so this process of things accumulating and then getting bigger and bigger, kind of snowballing, you might say. Until they form planetesimals. So these are like smaller planets. Just so we're kind of at a stable point in our solar system, right? We've got 8 planets, and we're probably nothing much is going to happen for a very long time. But you might have 100 planetesimals or 1,000 planetesimals at some point in your solar system, and they're still slowly knocking into each other and getting big, glomming into bigger and bigger things. Those eventually form the final set of planets. Okay. So gas giants formed by first all these ice particles that were doing the same thing in the outer solar system, forming tiny solid objects, tiny rocks, frozen rocks in the outer solar system, built into large planets out of ice and rock. But they still had lots of gas out there. There's lots of hydrogen that wasn't in a hydrogen compound, and that doesn't want to get captured. Hydrogen doesn't form rocks, it's a gas. Same thing with helium. And so there's a lot of matter out there in the form of gas that would not build into these planets. But once they got big enough that their gravity could hold on to the hydrogen gas, then they would start capturing the hydrogen gas. Jupiter did that first. And got most of the available hydrogen and helium. Notice that the Earth still isn't big enough to hold on to hydrogen and helium. If you release a helium balloon, it just goes straight up. And if you popped it, the gas would leave the atmosphere. Our planet is still not big enough to hold on to hydrogen or helium. Either one of those would leave. Now, hydrogen is bound up in water molecules, and so it's tied to oxygen. So that keeps those hydrogens on Earth. But if you just had free running hydrogen, like they made the Hindenburg out of, right, the one that burned, that stuff would just leave Earth. And so, but not Jupiter. Jupiter's gravity is strong enough to hold on to it. And so, so Jupiter swept up most of that stuff, and that was floating around in the outer solar system, and became the biggest planet. So we talked about how the inner planets form mostly out of rocks and metals. So we can look at planetary surfaces and get their age, and we can do that in two ways. One is by radiometric dating. So one is using radiometric dating, which is using the half-lives of radioactive isotopes. A few of these I've written down over here. These are just out of your book, but I'm just going to write them. Well, if I can find them. So samarium-147 has that lambda 1/2. So what I wrote there was a lambda. That's the Greek letter for L. And so it's L for life and half-life. So it's 106. The B is billion, so 106 billion years. So the half-life of samarium-147 is 106 billion years. Uranium-238 has a half-life of 4.47 billion years. This one's about the age of the Earth. And so however much uranium-238 the Earth started with, it now has about half of that, right? Because we've waited 4.47 billion years. And so half of it's gone. There are others. Rubidium-87 has a 48 billion year half-life. There are lots of isotopes that will allow us to estimate the ages of surfaces. And so this is one way to do it. The problem is, of course, to do this, you have to land on the surface and grab some rocks, right? And we haven't done that very many times. We do get rocks that are delivered to us as meteorites. Meteorites are the little rocks that formed in the very early solar system. And so when we take a radiometric dating of a meteorite, it's telling us how old the solar system is. The oldest rocks we have are about 4.56 billion years old. And that's what we get out of meteorites, about 4.56 billion, older than any rocks on Earth. We typically say the age of a rock is the times, the matter's been there forever, but the age we consider of a rock is the time since it was last melted. So on Earth, that usually means since it was recycled into lava, which we'll talk about how that works on the Earth. But it can also be just eroded away on the surface by a river running over a rock for 1 million years or something like that. So, so there are two ways of measuring planetary surfaces. One way is just this radiometric dating that we talk about. And the second way so the more craters you have, if we assume that these little rocky objects were all over the solar system, then everybody who's been getting peppered by meteors or asteroids at about the same rate since the beginning of time, or at least since the solar system formed. And so if I show more craters than you do, right? If this is surface A, and this is surface B, right? This is surface B. A is younger because it has fewer craters per square mile, right? Fewer craters per area. Sorry, there's a little glare on that. But so this is an older surface, and this is the younger surface. And when we did this on the moon, we were able to grab samples of rock from these different areas, and so we can calibrate them. So we say, if you have this many craters per area, you're this old, because we can do a radiometric dating on those rocks, or if you have this many, you're this old, and so on. And that allows us to go to other planets or moons and look at their crater density and tell how old the surface is. This allows us to then go to like Jupiter's moon Callisto or some other moon and just look at the density of craters on its surface and say, oh, this surface is about this old, because that's what the moon would, some area of the moon has about that crater density. Mars has a very low density of craters compared to the moon because it took Mars a lot longer to cool off. Okay. So planets can rejuvenate their surfaces if they have some kind of an active geology. And the way they do that is typically by having a hot interior. We still detect a little warmth in Mercury and Mars, but very little, and certainly nothing compared to these guys. Earth and Venus both have very active geologies. So if you have an active geology, you're having volcanoes which run out on the ground and erase your craters. You can have, you can also have weather and things like that, not necessarily related to a hot interior, but that can also cause erosion. But planets with an active geology will typically erase their craters on a short time scale, short geologically speaking. So, or they can be tidally heated like Jupiter's moons, Io and Europa. We talked a little bit about those. Io and Europa are getting sort of steadily squeezed by Jupiter as they orbit it. Io orbits Jupiter about once every 24 hours, and Europa like twice that. So they're getting this squeeze constantly. Io is the most volcanic planet, or I should say, most volcanic object in the solar system. And it's way less massive than our moon. It would be way cooled off by now if it had just been set out there like the moon was, with nobody squeezing on it. But because Jupiter is squeezing it so much, it's constantly got volcanic activity going on. It's spewing out volcanoes daily. Io volcanoes. All right. I think that's all I had on chapter 7. So chapter 8 is, I lost my notes. So we're going to take a little closer look at some of the planets, and we'll start with the one we know the most about. So I'm going to tell you stuff I think you know already. So here's the Earth. So can anybody, if this is the Earth, can anybody tell me what this inner region is?
The core?
Yeah, the core. And what's this one?
The mantle?
Yeah, the mantle. And what about the outer layer, the crunchy surface?
The crust.
Crust, thank you, great. So most of us have learned all this stuff, and it's pretty good. It's pretty accurate. There are a few little things that happen here. These are actually sort of compositionally different. And so I gotta pull the numbers out of here. So give me a second here. So the crust is somewhere between 2 and 50 miles thick. So it's just the very top, right? The mantle is 1,500 to 2,000 miles. And the core is about 2,000 miles in radius. So it's about 4,000 from here to here. And so the total diameter is about roughly speaking, is about 8,000 miles. Notice this crust is just negligibly small, right? 50 miles compared to 2,000 miles. It's a 40th as thick as this. In fact, if I had drawn it just with the outer black line, that probably would have been a better representation of it, right? We always think of it as being thick, but it's really not compared to everything else. It's quite thin. So who can tell me what the density of water is in any units? Probably took a physical science class in middle school where you learn that. Anybody?
Is it 1?
It is 1. Very good. And so we use the Greek letter rho for density. I don't know why. It's 1 gram per cubic centimeter. And if I can find a ruler here, right? A centimeter is not the tiniest, but the second tiniest gradation on there on a ruler. And so if I made a cube out of that, right? And so here's my large version of that, right? If I made a cube like that, 1 centimeter on a side and filled it with water, it would have a mass of 1 gram, right? And that's so density is mass divided by volume. And so we talked about it before. It kind of gives you a sense of how much matter is per volume, right? Lead is very dense. Air is styrofoam, not so dense, right? And so often we're comparing stuff to water. And so for comparison, the density of the crust of the Earth is about 3 to 3.5 grams per cubic centimeter. It's typically, if you just pick up a rock off the ground, that's the density of the crust rocks. any rock you pick up off the ground is going to have a 3 to 3.5, roughly speaking, density. If I want to know the density of the mantle, that varies from 3 to closer to 5. And so that's more of a metally type density than a rocky type density. And finally, the density of the core is about 10 grams per cubic centimeter. And that's like, I think, aluminum, copper, and this one's like lead. So the core is iron and nickel, mostly. The reason it has the density of lead, which is much more dense, is because it's under enormous pressure. And so even though it's iron, it has a much higher density than iron on the Earth's crust, or significantly higher, not hugely higher. This guy is metal compounds. And this is just the top of the rock. And so the composition of these things is different. We find through techniques I'll talk about later that all planets are sort of like this, that they're really dense stuff is at the center, slightly less dense stuff is in the middle, and the lightest weight stuff is at the surface. This tells us that the planet's likely formed molten or liquid. When you have a liquid, the densest stuff falls to the bottom. Now, not every single thing that's dense fell to the bottom because the Earth cooled off and more stuff was still coming. At least its crust did. But if you just look at the Earth as a whole, with the densest stuff in the center and less dense stuff going going towards the surface, that's a picture of something that formed as a liquid. And all the planets have this. We have sort of ways of learning the density distribution of planets. And they all have more or less the same structure, where the dense stuff is in the middle and the lightest stuff is on the top. We think of rock as being sort of the densest stuff we have. And so it's hard to imagine that, rocks can float, but they can float if they're sitting on top of metals. You can get a pool of mercury, which is a liquid metal at room temperature, and set a rock on top of it. The rock will just float on top of the mercury. And that's kind of what's happening on the Earth. The continents are floating. And so if you have this picture, so if I have a continent here, I'm just going to draw a crazy continent, right? There's my continent. Right? And then below the continent is the mantle. And it turns out that the mantle can move and carry the continent with it. And that's how we get continental drift. They used to think that that wasn't a thing, that couldn't be possible. But now we can put little GPS units on stakes in bedrock and on continents, and we can watch them geologically move over time as earthquakes happen and so forth. All right, let me just back up a little bit and come back into that for a second. So there are there are a million different types of rocks. If you've ever been a rock hobbyist, there are many different types of rocks. But we break them up into sort of three basic classes. And the first one is igneous rocks. And those just form from whatever comes out of volcanoes. And so when a volcano erupts, it can have all kinds of different minerals in it, but anything that forms from something that came out of a volcano is called igneous rock. The second one is sedimentary rock. If I recall correctly, much of Oklahoma was at one time an ocean bottom. Certainly there are places right over by Clinton where you can walk out and find fossilized shells just on farmland. From I think the Permian era, the Peruvian, I can't remember. So sedimentary rocks form from sediment. So, you know, if an ocean has been there a long time, things die and dust falls on the ocean and settles to the bottom, and that stuff eventually builds up and gets compressed and forms rocks. And so, you know, like you've probably heard of sandstone. We get lots of sedimentary rock. If you just drive down a road where there's a cutout to make the highway, you'll see on the sides of that sedimentary rock that you're going through. And finally, 3 is metamorphic rock. Metamorphic really just means new form, new type. And it usually happens when you take a sedimentary rock or an igneous rock and somehow get it hot, not to the point of melting, but to the point of changing it somehow. And so those are your 3 basic types of rock. I think that's all I wanted to say about that. Okay, maybe the last thing I'll talk about is getting back to this issue. Plate tectonics is the motion of plates in the Earth's crust. So the Earth's crust has these plates on it. I don't know how to draw it. So for example, if you look at South America and Africa, they're moving apart. It's not the first guy Alfred Wegener, I think he's a German guy. He noticed that, I think we talked about this before, that if you look at the east coast of South America and the west coast of Africa, they kind of look like they match up. And so he suggested that maybe they were matched up at one point. And then he went through a whole bunch of grief because nobody believed him. But eventually, he sort of convinced the world that he was right. This is what usually happens in science, or often happens in science. Somebody nobody's ever heard of has an idea, and they end up having to defend it by themselves for a long period of time. Then it becomes like common knowledge, like everybody knew it from the very beginning anyway. And this is one of those examples where he was just really roasted for a long time. And finally everybody said, oh yeah, we've known that all along. And so what happens is, like I was saying earlier, these plates sit on the mantle below, and the mantle is flowing. So imagine it's hard to imagine this unless you really understand the time scale. But suppose I have a pan of water, right? I'm heating. That looks like Oklahoma. That's not. I wish I could heat Oklahoma right now, but that's not what that is. All right. So here's water. Right, and I'm heating this pan of water, and so the water gets heated at the bottom and it rises. And you can get these cycles where it rises and it cools itself at the surface and then comes back down again. And so these are like thermal currents or eddy currents or something like that in the water that have to do with the fact that the water is being heated from below and is flowing. And so if you were sitting on the top here, if you have a boat, here's my boat, and it's sitting on the top here, these two boats are going to go in opposite directions because they're sitting on the water that's flowing like this, and so they get pushed to the outside. And this is sort of what happens in the Earth's mantle. If you look at the Earth, right, here's the crust, and here's the mantle. The mantle is very hot. The outer mantle is actually liquid iron. There are actually two mantles. There's an inner mantle and an outer mantle. The outer mantle is liquid iron, and it's heating the outer core. No time for you to stop. The outer core is very hot, and it's heating the mantle from below. And so even though the mantle is a solid, over long periods of time, it flows. And these continents that are sitting up on top flow with the mantle. It took us a long time to figure out that that's what's going on, but that's exactly what happens. And we can now put GPS markers on all these continents and tell how they're moving relative to the stuff below them. We have other evidence of how volcanoes form, which I'll talk about a little bit next time. So that's plate tectonics on the Earth. It's due to the motion in the mantle, because the mantle is being heated from the bottom by the core. As the Earth cools off, the Earth is just like a hot potato that's floating in a cool room after it's been taken out of the microwave. They cool from the outside in, and we'll talk about that more later. But eventually the Earth will cool off, and there'll be no more geologic activity, no more volcanoes, no more earthquakes, and so no more erosion, or much less erosion. And so we'll get much less interesting when that happens. Our geology will be a lot less interesting. All right, I think I'm going to stop at that point. You can hang around if you have any questions. Keep in mind that if we have class tomorrow, we'll have a test tomorrow, just whatever the first day back is. And I'll try to put together a quiz for the end of the week. That's all I got.
Professor?
Yeah.
Is there some type of simulation that shows what the Earth might look like if the tectonic plates keep moving in the direction?
I don't know. It's certainly true that there are lots of programs that are doing all kinds of simulations, like this thing I was talking about with the planetesimals and how solar systems form. I was seeing simulations on those 30 years ago, a long time ago. But I would just Google it, see if you can find that out. That would be that'd be interesting to know. But I don't know the answer to your question is I don't know.
Okay.
Any other questions?